Welcome to Chapter 4. This is a chapter that deals with basics of probability. And make sure you read the chapter. There's a lot of good examples to follow, and we'll hit quite a few here that will definitely help you with the homework assignments for this section. Probability is something that by this time we all have a basic understanding of what it is. A really common question is, if you toss a coin, what's the probability that you get heads? And the answer would be 50% or 50-50. And that's because one side has tails, the other has heads. So the probability that you get heads is there's one side that has heads out of two total sides, or 1/2. The rare event rule for inferential statistics is something that we'll come back to in a later section, but it says that if, under a given assumption, the probability of a particular observed event is extremely small, then we can conclude that the assumption is probably not correct. And some fundamentals of probability are that an event is any collection of results or outcomes, and then a simple event is a single outcome that cannot be broken down any further. Sample space is when we list all possible events, and then the notation that our textbook uses for probability is P of A. And P of A, or P of something, denotes the probability of that event A occurring. There's a probability that we can solve for that's called a relative frequency, and this is where we can actually do a trial. So for instance, if we were to actually toss a coin 10 times and find the probability of H, which is the probability of getting heads, then when we're doing an actual experiment or trial, then the probability equals the number of times that that particular event occurred divided by the total number of times that we did the trial. However, what we're faced with, since we can't usually do a trial, is we're faced with classical probability. And so with classical probability, all of the events must have equally likely outcomes. And so the probability that something would happen is we take the number of times that A can occur and divide it by the number of different simple events. And so an example would be, we would expect that the probability of heads equals 1/2 when tossing a coin. And then there's another type of probability that we have always seen discussed if we check the weather in the newspaper or watch the meteorologist on TV, and that's a situation that uses subjective probability. In subjective probability, they estimate the probability that something will happen by taking information of relevant circumstances and applying it. So an example is when meteorologists try to estimate the probability that rain will occur, and they might say there's a 60% chance of rain. Well, what they're saying is that when these types of weather conditions occur, in 60% of the cases, rain will happen. So it's not really necessarily can be taken as a strong chance, because as we all know, we've seen 60% chance of rain forecast and then no rain at all. When we repeat the relative frequency probability over and over, the probability will actually start to begin to approach the actual probability. So when we're conducting a trial and we want to see what's the probability of tossing a coin and getting heads, well, the more times we toss the coin, if we only did it 10 times, it's possible to get tails each time. But if we continue maybe 1,000 times and repeat this, then over the course of that, we will finally approach the actual probability of 1/2. So a probability estimate that's based on only a few trials can be significantly off. And so with a large number of trials, the estimate tends to be much more accurate. When we have outcomes that aren't equally likely, that means that not all outcomes are likely to occur, then it would be incorrect to conclude that the probability of passing a test is 1/2 or 0.5 because we say, well, we either pass the test or not. And that doesn't really make sense. It's not really 50-50. So the actual probability really depends on a lot of different variables. Like, are you really prepared for the test? Is the test extremely difficult, or is it an extremely easy test? And so that would significantly affect the true probability of passing the test. And then here's some probability facts. The probability of an impossible event is 0. And then the probability of a certain event is 1 or 100%. So any probability should range between 0 and 1. And so remember that decimals, for instance 50%, can be written as a decimal 0.5. So the probability has to be a number between 0 and 1. It has to be a positive decimal. The complement of a probability or of an event A occurring is denoted as A with a bar above it. Now the complement of a probability does not mean that we're saying that's a really nice probability. What we're doing is we're trying to come up with the opposite of that event, or it's the probability that the event A will not occur. So if the probability that A will occur is known to be 60%, then we can easily find the complement of that event, or the probability that A will not occur, by noticing that all probabilities have to add up to a total of 100%, and we subtract 60% from that and we get 40%. Likewise, if we work with the decimal equivalents, then if the probability of A is 0.6, then the probability that A will not occur is 0.4. So let's just practice, and we're going to express the indicated degree of likelihood as a probability value between 0 and 1. So all of our answers should be written in decimal form, not percents. So when flipping a quarter, there is a 50-50 chance that the outcome will be heads. So we want to represent the 50-50 chance as a probability. And so that would be 1/2, and 1 divided by 2 equals 0.5. So that's a pretty easy one to convert. Or you have 1 chance in 5 of guessing the correct answer. So 1 out of 5, we divide 1 by 5 and we get 0.2, and that's the correct probability. And then finally, you have a 1% chance of getting a date with the person who just entered the room. So to convert this percentage to the decimal, a shortcut is to move after the number 1 2 times. So we move 2 times to the left, which causes us to put a 0 in front of the 1, so we get 0.01. Or, when it's written as a percent, you can always divide the number by 100 in your calculator, and the calculator will give you the correct decimal. So we could take 1 divided by 100, and that equals 0.01. This would work for any percentage that we want to convert. So if we had 15%, we would take 15 divided by 100 to get the decimal equivalent of 0.15. On page 142, let's look at example 4. When studying the effect of heredity on height, we can express each individual genotype as AA, both capitalized, or capital A little a, or little a capital A, or little a on an index card. So then what we have here is 4 different index cards. We're going to shuffle the 4 cards, and we're going to randomly select one of them. What is the probability that we select a genotype in which the 2 components are different? Well, if we're looking for the 2 components to be different, which of the answers above are we looking for? Well, if they're different, that means that we're looking for one of them to be capital and one of them to be lowercase. And if we look above, there's 2 different cards that have that. So we have 4 total outcomes in the sample space because we have 4 total cards. Among the 4 outcomes, there are exactly 2 in which the 2 components are different. So we can use the classical approach to get the that P of the outcome with different components is equal to 2 cards out of 4 cards total, and that divides to equal 0.5. Here's example 7 on page 143. Find the probability that when a couple has 3 children, they will have exactly 2 boys. Assume that boys and girls are equally likely, and the gender of any child is not influenced by the gender of any other child. Well, we need to correctly identify the total sample space, which means we need to list all the different outcomes that could occur if these people want to come up with exactly 2 boys and they have 3 children. So the sample space consists of 8 different ways that 3 children could occur. Now remember, birth order is important here, so I've listed the sample space here using boys or girls. So the first thing that could happen is they could have a boy, then a boy, then a boy. Or they could have a boy, then a boy, then a girl. Or they could have a boy, girl, then a boy. Or a boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Or girl, girl, girl. So the trick to coming up with a sample space here is to come up with some type of a pattern so that you don't leave any of the different events out. Now in blue, I have highlighted the events that pertain to the probability that we are solving for. Remember that in the question it says we're solving for the probability that when a couple has 3 children, they have exactly 2 boys. Exactly 2 means they don't have 3, they don't have 1. So I've got the 3 situations highlighted where there's exactly 2 boys and 1 girl. And so there's 3 events out of 8 total in our sample space. So the probability of getting 2 boys and 3 births equals 3 out of 8. And when you divide 3 by 8 in your calculator, you get 0.375. So on your test, what you'll likely do is give me the decimal answer and not the one that's written as a fraction. Here's another example taken out of your textbook that refers to probability. In a study of 420,095 cell phone users in Denmark, it was found that 135 developed cancer of the brain or nervous system. Estimate the probability that a randomly selected cell phone user will develop such a cancer. Is the result very different from the probability of 0.000340 that was found for the general population to develop cancer? What does the result suggest about cell phones and say cause of such cancers as has been claimed before? So let's set up this classical probability. So what are we solving for? We're solving for the probability that a cell phone user gets cancer. So let's use, I've highlighted in red the important numbers. So just search for the numbers in the problem. 135 developed cancer. So let's go ahead and put that in the numerator of our fraction. And the denominator, always search for the total. So in their study, they had a total of 420,095 total cell phone users. Next, divide 135 by 420,095 in your calculator, and you get the probability of 0.000321. Now notice that what I did is I went out to 3 significant numbers that followed the zeros in front. So I didn't round it to 0.0003. I kept going to 3 significant digits. And that's a practice that you'll want to apply when you solve these probability problems when you get very small numbers. So let's compare that now to the other probability in red up there. That was the probability that somebody from the general population gets cancer. That means they don't have to be a cell phone user. Well, if we compare these 2 probabilities, they're very, very similar to each other. And so the cell phones then do not appear to put people at a greater risk of developing cancer than the risk that just already exists in the population. Here's another example where we can set up a classical probability. The U.S. General Accounting Office tested the IRS for the correctness of answers to taxpayers' questions. For 1,733 trials, the IRS was correct 1,107 times and wrong 626 times. Estimate the probability that a randomly selected taxpayer's question will be answered incorrectly. So I highlighted the word incorrectly because that's the word that I want to put after my P, or probability. So I'm searching for the probability of incorrect. And so that means I need to search for the number that goes with the word incorrect up in the word problem. So if I look up in the word problem, the number that's associated with being wrong is 626 times. So I want to use 626 as my numerator. The denominator is always the total number of participants, or the total number in the trial, and so that would be 1,733 total trials. Next, divide those two numbers in your calculator and round it to 3 significant decimal places, and so we would round it to 0.361. So let's go ahead and look at the next step in this question. Is it unusual for the IRS to provide a wrong answer to a taxpayer's question? Should it be unusual? Now, when we answer these questions about unusual events, we need to always remember that an event is unusual if it's less than or equal to 0.05, which is 5%. So if you remember the empirical rule, and we draw the normal bell-shaped distribution curve, and remember that 95% of your data is going to fit between 2 standard deviations, and so that leaves 5% to fall outside of that. So anything that's smaller than 5% is going to be in the tails or extremes of the empirical curve. So let's look at the probability that we got as our answer. It was 0.361. That's about 36%. So that means that, is it unusual for the IRS to be wrong? Well, since 0.361 is greater than 0.05, it's not unusual. And so that would not be very comforting to me to know that it's not unusual for the IRS to provide wrong answers. So how do we round off our probabilities, since we're going to be getting a lot of decimal answers that don't terminate? When expressing the value of a probability, either give the exact fraction or decimal, or round off final decimal results to 3 significant digits. And so that was expressed earlier, where we had that decimal that had the 3 zeros and then the numbers began. So when the numbers finally started, I went out 3 different numbers. When a probability is not a simple fraction that's easily understood, like 2/3 or 5/9, so what if we got 19 out of 350? Then we need to express that as a decimal so that the number can be better understood as a percentage. All digits in a number are significant except for the zeros that are included, and the zeros help give us proper placement of the decimal point. So whenever you're determining significant digits, it's always after the zeros stop. And then let's just discuss unusual events once more. We consider an event to be unusual if the probability is less than or equal to 0.05. So this corresponds to the event being more than 2 standard deviations from the mean. Sometimes we use a stricter way to compare, and so we might be asked to use the value of 0.01 as being unusual. So that would be comparing it to 1%. Now, another component of probability questions are odds questions, and they are very different in how we set them up. The odds against something occurring is the probability of A complement divided by the probability of A. So let's redefine that in layman's terms. That would be the probability that A doesn't occur divided by the probability that A does occur. Notice that in both of the numerator and the denominator, we are not putting the total trials in either place. The odds in favor of something occurring would be the probability that A does occur divided by the probability that A does not occur. And then another thing that we'll look at in this section, because they put in a lot of different questions related to gambling and betting, is payoff odds equals net profit compared to amount bet. So the use of the colon there is like using a fraction bar. And so we tend to use the colon instead of a fraction bar for odds. Here's an example of an odds situation. If you bet $5 on the number 13 in roulette, your probability of winning is 1 out of 38, and the payoff odds are given by the casino to be 35 to 1. So let's discuss a few of these numbers first before we look any further. So we're betting $5 on the number 13. Why does it say the probability of winning is 1 out of 38? Well, that fraction itself means that there's one number 13 on the roulette wheel, and 38 must mean that there's 38 slots total on the roulette wheel. And then the payoff odds are given by the casino as $35 to $1. So let's look at the first question. Find the actual odds against the outcome of 13. So odds against means we're searching for how many numbers are not 13 on the roulette wheel, because that would be against 13. And then we use a colon, and on the other side of the colon we put the opposite. How many numbers are the number 13? So we know that there's 38 total numbers on the roulette wheel, so we would have 37 to 1 as being the actual odds against the outcome of getting 13. Notice that when we have 37 to 1, if you add 37 and 1, you get 38 total. So when you set up an odds fraction, you should check it, because if you add the two numbers together, you get the total, whereas in a probability question, the total is always on the bottom of the fraction. Let's look at the second step. How much net profit would you make if you win by betting on 13? And because we're told that the payoff odds against 13 are 35 to 1, let's go back and find that information that talks about payoff odds that was on the previous slide. We learned that payoff odds equals net profit to amount bet. And so they're giving us 35 to 1. So if we label the left side, that means it equals net profit to the right side is amount bet. So to correctly read that, it means there's a $35 profit payout for each $1 bet. Now how much did we bet? Well, we bet $5 on the number 13. So we multiply 35 by 5 and we get a net profit of $175. You also get back your $5 bet that we bet, so the total amount won would be $175 plus 5, or $180. If the casino were operating just for the fun of it and the payoff odds were changed to match the actual odds against 13, how much would you win if the outcome were 13? Well, this is why casinos make so much money, because their payoff odds never match actual odds. In Part A, we found that the actual odds against the outcome of 13 would be the numbers that aren't 13 compared to the numbers that are 13. So we got 37 to 1. And so in that situation, we would be paid $37 for each $1 bet. So if we bet $5, our net profit would be 37 times 5, or $185. Then you could also add the $5 back to get $190 as your total win. Here's another gambling situation. So we get to look at a lot of fun things that maybe you've never been involved in before, but now you'll have a little bit of understanding about them. The probability of the horse Out of Here winning the 129th Kentucky Derby was 1 out of 50. What were the actual odds against Out of Here winning that race? So let's look at the first fraction that we have highlighted in red here, 1 out of 50. So what does that fraction mean? Well, if it's told to us that it's probability, then the denominator must be the total horses. So 50 total horses. And the numerator 1 must mean that there's one horse, and that horse would be out of here. So his probability of winning is 1 out of 50. So now let's set up the odds. The odds against out of here winning. Well, then the odds against would mean we want to know first the number of horses that are not out of here, and then we want to compare that on the right side to the number of horses that are out of here. So from the probability fraction that we were given, we know that the total horses in the race is 50. So remember that when we set up the two numbers in our odds fraction, the sum of the two numbers should equal the total 50. So we never put 50 in the fraction. So then the odds are 49 to 1. 49 is the number of horses that are not out of here, and then we compare that to the one horse that is. When the horse Funnyside won the 129th Kentucky Derby, a $2 bet that Funnyside would win resulted in a return of $27.60. So how much net profit was made from a $2 bet on Funnyside? Well, we got a return of $27.60, so let's subtract our $2 bet. And we get $25.60, and that would be our net profit, which is profit over and above what we bet. What were the payoff odds against a Funnyside win? Payoff odds, remember, by definition, equals net profit to amount bet. Well, we just figured out that the net profit is $25.60, so we have 25.60, and then the amount bet was $2, so 25.60 to 2. Now from here, what I'm doing is looking for a way to reduce this fraction 25.60 to 2. So my suggestion is to use division first and see what you get. So 25.60 divided by 2 equals 12.8. Now the problem with 12.8 is that it is a single decimal and it's not a fraction. So most of these calculators, and the ones that I recommend that you use, do have fraction conversion buttons. So when you have the decimal 12.8 on your calculator screen, what you need to do is type second and then type the PRB probability button, because above that it says F to D, fraction to decimal, and vice versa. So when I do that, second PRB, my calculator now says answer, convert fraction to decimal. I'm going to say yes, so I hit equals or enter. And now it looks kind of funny. My calculator screen says 12 and 4/5. It's a mixed fraction. So we have one more thing to do. We want to convert this mixed fraction to an improper fraction. Now you might remember from your math classes in elementary school that a quick way to do that is you take the denominator 5, multiply by 12, and add the numerator 4. 5 times 12 is 60. 60 plus 4 equals 64. So then we get the improper fraction 64 to 5. Or, to get it in your calculator, type second ABC button. The ABC button is directly below the PRB button. So second ABC, now it says answer convert a mixed fraction to a improper fraction. So let's hit equals. Now your calculator should say 64 over 5. And so that gives us the payoff odds against this Funnyside win is 64 to 5. Based on a preliminary wagering before a race, bettors collectively believed that Funnyside had a 2 out of 33 probability of winning. Assuming that 2 out of 33 was the true probability of a Funnyside victory, what were the actual odds against his winning? Well, the odds against his winning would be the number of games lost to the number of games total that were won. So I have 31 to 2. So how did I come up with 31 games lost and 2 games won? Well, you have to look up in blue where it says that he had a 2 out of 33 probability of winning. Now obviously there aren't two horses named Funnyside, so the number 2 must represent something else. And what it represents is 2 wins out of 33 total games. And so if we go down then, the number of games lost would be 33 take away 2, which gives you 31. And then we compare that to the number of games won, which would be 2. Again, if you add the two numbers together in your odds, 31 plus 2 equals the total 33. If the payoff odds were the actual odds found in Part C, 31 to 2, how much would a $2 ticket be worth after the Funnyside win? Well, the actual odds in Part C, we came up with 31 to 2, so that would be $31 profit plus the original $2 bet back, or $33 total.